Okay. Thank you, Mr. Chairman. Good morning, everybody. First of all, I would like to thank the organizers to give me an opportunity to have a talk here on this wonderful conference. And as you can see, I will speak again about PMN and about our recent results and evaluations of terahertz and infrared spectra and also microwave. Most of work was done by my colleague Dmitry Nushny, who carefully measured terahertz and infrared and evaluated with mean field theory with Jan Petzelt. And microwave data were obtained by Viktor Bovtun and Martin Kempa under guidance of Jirka Hlinka, and Helen gave us some hyper-Raman data on this compound. So quickly, outline of my talk. You know already what is PMN, so introduction will be very short, and then I will focus mainly on explanation of high temperature dielectric properties above Bern's temperature, the Curie-wise behavior, where is it coming from, whether it can be explained with the phonons, and I will show that it can be really explained, and that there is a soft mode which shows anomaly at 400 Kelvin at this T-star temperature. So there is a typical example or typical picture of relaxors, and PMN is typically representative of relaxor, showing shift of peak permittivity with frequency, and it was explained already many years ago. For example, in these two papers, Wieland or Tagantsev, showing that there are some dielectric relaxations in below phonons which broaden on cooling and practically explains this broad distribution or this broad dispersion in permittivity. Wieland measured as well permittivity up to 800 Kelvin, and it showed that practically the high temperature permittivity follows Curie-wise law, but below Bern's temperature, it was assumed that around 600 Kelvin, polar cluster appear, that around this temperature there is seen some deviation of permittivity from this Curie-wise law. And note here that this extrapolated temperature is 400 Kelvin. And so question is how to explain this behavior. I will take my laser, is better. And because this high temperature behavior has, or this permittivity does not exhibit any frequency dependence, so one can assume that there must be some excitation at much higher frequencies, let's say above microwave, and it means phonons. And Peter Gehring and Wakimoto studied phonons using inelastic neutron scattering, and they found really phonon softening at high temperatures, then and at below freezing again some hardening, but in this temperature range there was no proper signal because there is a waterfall effect. I will not speak about it. But the important point is that this phonon softening, which follows Cochrane law, does not explain completely the Curie-wise behavior. So this softening must be much faster, and then it can explain the Curie-wise behavior. And so there must be another excitation below this phonon, and our chairman, Sergei Vakrushev, found some hints of this second phonon softening below this phonon's frequency, but it was very difficult to see it in neutron scattering because it is practically overdamped. And already 12, 13 years ago, we investigated PMN crystals or ceramics or thin films, and here is an example of a study of PMN thin film on sapphire, spectra of the sapphire show nice transmission. It means that we have interferences in sapphire, but in thin film we see some absorption minima here showing phonon frequencies. And note the phonons are split, and practically they are split at all temperatures. And in that time we explain it by appearance of polar clusters below Barron's temperature. And then we had soft mode, which is same like this neutron scattering. These red points are from neutron scattering papers. And the soft mode softens only slightly. And then there is a saturation and hardening on cooling at lower temperatures. But we saw another component at lower temperature or at lower frequencies, showing that in that time we call it central mode or second component of the soft mode. But it is seen only up to Barron's temperature. So we explain it in that time as well, that we have polar clusters and symmetry is broken below Barron's temperature. But later there are two papers from Bernard Helland and Jirka Hlinka who studied hyper-Raman scattering. You know, in hyper-Raman you have same selection rules. Like in infrared spectroscopy, you can see the polar phonons. And what they found, practically two soft modes in high temperature range, and this this mode corresponds to mode seen in neutron scattering. But there is another component which is much softer, and it goes to 0 at 400 Kelvin, and in this range it's not seen properly because of difficulties in the experiment, but at low temperature it is again seen. So it looks like that there is a soft mode like this, and this second mode here was explained like originally, or infrared inactive mode, F2G symmetry, which is seen in Raman scattering, and due to coupling of these two modes, it becomes as well infrared active finally. And there is another component of the soft mode here, hardening, same like in our previous infrared spectra. So note here, this is originally non-active infrared mode, but it becomes coupling. It is coupled with the soft mode, this one, and therefore it appears in the spectra. Same is in PMT as well. So it looks like general behavior in relaxors. Some time ago, we investigated infrared reflectivity spectra, and we see practically splitting of all phonons. It means that it looks like that we don't have a cubic symmetry. You know, PMN is macroscopically cubic, and so there should be only 3 polar phonons, and we see 3 bands, but each of them is split. And in that time, we used Bruggemann effective medium approximation that it took into account that practically the crystal PMN consists of polar nanoregions or polar nanodomains, which there is no non-polar matrix, only such domains, which have a permittivity, long polarization, some value. 1/3 of the value has this permittivity, and 2/3 of the value of the volume has permittivity different. And this under this restriction, we were able to calculate effective permittivity, which is finally responsible for such shape of reflectivity. And really, we obtained anisotropic permittivity in such polar nanodomains. And I have to stress that such polar nanodomains could be just dynamic. They can exist just in sub-picosecond scale. But the infrared spectroscopy is sensitive on this broken symmetry. So, and we can see that each mode is split, and we can explain such splitting as well in infrared spectra. But this paper was published 12 years ago, and we just investigated low temperature properties, and last year we focused on high temperature or on all temperatures, that we have spectra, infrared reflectivity spectra from 10 Kelvin to 900 Kelvin. And looks like that there is no dramatic change. But when we evaluated the spectra, and there is a complex, or there is a optical conductivity calculated from which is related to dielectric losses, the peaks correspond to phonon frequencies, and the data, low frequency data are also from terahertz spectra, show clearly splitting of the modes, and there is a frequency, temperature dependence of all phonon frequencies showing splitting, and in this way we were able to calculate permittivity along polarization, which has A1 symmetry, and the permittivity or phonons of E symmetry give such permittivity. You note that here we have permittivity up to 1,000, and in this case only a few hundred. And separated optical conductivity in both directions goes such response. Note that A1 response is an underdamped phonon which shows softening and hardening with temperature, and E mode is heavily damped or overdamped at some temperatures. So the E mode softens. This is the same mode seen like in hyper-Raman spectra, and it shows minimum at 400 Kelvin, and again some hardening. And the higher frequency component, in this case it is not this F2G mode interpreted in Raman scattering, but it is just second component of the soft mode, which shows small softening. It is seen also in neutron scattering, and then the hardening. And some other modes appear at below freezing temperature because the symmetry can be lower. But important is because this soft E mode is overdamped, then physical quantity or the better meaning has phonon frequency square divided by gamma, and it shows peak in losses frequency. And this phonon frequency goes to 0 at 400, or to few wave numbers at 400 Kelvin, and then there is again hardening. And this follows very well Cochrane law, and then it explains as well, when we calculate it from this phonon contribution permittivity or reciprocal permittivity, we can see nicely that there is it follows Curie-wise behavior. So this Curie-wise behavior shown before already by Cochrane or by Wieland, it can be explained by this phonon softening. And then there is some deviation below 600 Kelvin in experiments because some relaxations appear. And note as well that this anomaly at 400 Kelvin looks like ferrotic or some phase transition at T-star temperature. And this anomaly was seen as well, let's say, if you plot temperature dependence of integral intensity of diffuse neutron scattering, shows as well some change at 400 Kelvin, or Brahim Kill published temperature dependence of lattice constant showing below freezing increase, then stable lattice constant, and then increase. So it looks like that there is really some phase transition. It's question, what is it? Prosandiev published a few years ago the theoretical paper explaining that here at high temperature we have spherical glass, the light is displaced in any directions, and then below this temperature there is quadruple glass, that some displacement is preferable. So practically the picture is that we have E mode which softening around 400 Kelvin, and then below phonons we have an additional relaxations. I will have no time to speak more details about relaxations here, but they are at high temperatures somewhere in microwave range, and these modes or these relaxations soften or slow down On cooling, one of the component follows the Vogel-Fulcher law, and second one, Arrhenius law. And I think that this behavior is general in all relaxors. Here I have an old picture from PMT showing in thin films as well, two components of the soft mode. In this case, we did not use the EMA, this effective medium approximation, that we did not see properly the softening here, but let's say just roughly fitted. But in PMT ceramics, again, we see the softening and hardening around 400 Kelvin. In this case, we were not able to resolve at higher temperatures this lower frequency component because it's everything very damped. It's difficult. And the same is in PST, but I have no time, so let's go to conclusion. I wanted to show that Curie-wise behavior above Berens temperature can be explained by lower frequency soft mode, and the soft mode has anomaly at 400 Kelvin, so some structural phase transitions appears. I don't know, is it really structural phase transition from rhomboidal to monoclinic phase, or from or from some glassy phase, but it is for future. Thank you.
Okay, thank you. Questions, please? If you don't mind, I'd like to make short comments. And excuse me, you carefully ignored our two papers where calculations were done actually by Roman Burkowski, who was my PhD student at that moment. It was demonstrated that upper and lower, let's say, modes has very different behavior in Q. So actually, this lower one disappear at Q about 0.15. So to discuss the real space picture, I believe it's a kind of obligatory to include this fact, because in other case, it looks like they are absolutely equivalent.
We cite your paper in,
no,
yeah,
it's not
but I had no time to discuss it here in more details.
Okay.
The point is that we measure only in Q equals 0, only.
Yeah, I understand.
Yeah.
Okay. Thank you again.
Thank you.
And now, Alexei Bokov.